Assalamu alaikum. Hello dear students. Today we will continue with the chapter 7 Vibrations and Waves part 2. By the end of this video, you will be able to define a wave and identify its characteristics. In the previous video, we have talked about a vibratory motion and we have characterized it by its period, where t in second is equal to delta t divided by n, its frequency, where f in hertz is equal to n divided by delta t, and we've recognized that t is equal to 1 over f. Also, such motions are characterized by their amplitude, which could be expressed as either a distance a or as an angle alpha. Let's start with our objective by observing the following video. Notice that the hand produces several perturbations or vibrations, but the perturbations doesn't stop. Each perturbation propagates or travels along the rope. This is what we call a wave. Then, we can define a progressive wave as a perturbation produced by a source of vibration that propagates through a medium, like sound waves and water waves. But do waves carry matter? To answer this question, let's focus on the movement of the red tape and the red ball as a wave passes by them. The red ball and the tape oscillates around their equilibrium positions without being dragged by the wave. Then, the wave doesn't carry matter, it only transports energy. In this year, we are interested in studying periodic waves. Let's have a look on such waves. The displacement axis represents the direction of the particle's vibration, while the distance axis represents the direction of the wave's propagation. Note that the maximum displacement of a wave is called the crest, while the minimum displacement of a wave is called the trough. Let's now list the characteristics of waves. Waves are characterized by their period, their frequency, and their amplitude. But these characteristics are imposed by the source of vibration. Then we can write that the frequency of the wave is equal to the frequency of the source of vibration. Note that the amplitude is measured from the rest position to either the crest or the trough, and the higher the amplitude, the higher the energy the wave carries. Waves are also characterized by their wavelength denoted lambda, which is the distance traveled by the wave during one period. The wavelength could be measured between two consecutive crests or two consecutive troughs, and it is expressed in meter in the SI unit. To convert from centimeter into meter, you multiply by 10 to the power minus 2, and to convert from millimeter into meter, you multiply by 10 to the power minus 3. Waves are also characterized by their speed of propagation v, which is the distance traveled by the wave per unit of time, and it is expressed in meter per second in the SI unit. Then we can write speed v is equal to the distance divided by time is equal to d divided by delta t. For one cycle, we can replace the distance by the wavelength lambda, and we can replace the duration of time by a period. But 1 over t is equal to the frequency of the wave, then this relation could be written as lambda times f. Now, to know what affects the wave's speed, let's watch together.
This relationship of frequency times wavelength equals wave speed holds true for all kinds of waves, water waves, sound waves, light waves, you name it. What's fascinating is that if you have a higher frequency, that necessarily means a shorter wavelength, and a lower frequency necessarily means a longer wavelength. Frequency and wavelength are inversely proportional to each other. You can't make one bigger without the other getting smaller. But notice that the product of the two remains the same. That is, the wave speed remains constant no matter what the frequency or wavelength. So, what determines the wave speed? Well, you know how it's easier to wade through a pool of water than through an equally deep pool of maple syrup? That's right. It's the medium through which you are traveling that determines how fast you can travel. The same holds true for waves. How fast waves travel depends upon, and only upon, the medium through which the waves are traveling.
Then, the speed of the wave is only affected by the medium in which it propagates. This helps us in understanding the relation between f and lambda. Some may ask, what happens if we increase the frequency of the wave? They think that since v is equal to lambda times f, if f increases, then v increases. But what about lambda? But actually, this is wrong. Since in the same homogeneous medium the speed of the wave remains constant, then we can write v is constant, so if f increases, then lambda will decrease, which implies that f and lambda are inversely proportional. In other words, for low-frequency waves we have longer wavelength, whereas for high-frequency waves we have shorter wavelength. Let's observe the following figure. For C waves, the speed of the wave depends on the depth of the medium. As the depth decreases, the speed of the wave decreases, and thus the wavelength decreases. All these can be summarized in the following conclusion. The speed depends on the nature of the medium, the frequency depends on the source of vibration, and the wavelength varies with the variation of either the speed or the frequency. We have mentioned the way of calculating the wave's speed, but what about the particle's speed? When a wave is generated, particles will vibrate. But the speed of propagation is different than the speed of vibration. The speed of vibration is calculated by dividing the distance traveled by the particle by the duration of time. If we focus on one cycle, we can notice that each particle covers 4 amplitudes during its movement during one period. From its rest position up to a crest, back to its rest position, down to a trough, and back to its original position. Then instead of the distance we can write, then the speed of vibration is equal to 4 amplitudes divided by a period of time. Now let's summarize the main ideas of this video. Waves are perturbations that propagate in a medium carrying with them energy and not matter. Waves are characterized by their amplitude A, their period t, their frequency f, wavelength lambda, and the speed v, where f in hertz is equal to 1 divided by t in second, and where v in meter per second is equal to the distance covered by the wave divided by the duration of time, or it is equal to lambda divided by t, or lambda times f. Thanks for your attention.